Assalamualaikum. So for today I will cover for subtopic 3.9, okay, which is the last part of chapter 3. Okay, previously we have covered from 3.4 to 3.8, which I explained about the introduction of the entropy and also the concept of the second law of the thermodynamics. So is much related with what we are going to do for this topic, which is isentropic efficiencies of the steady flow devices. So when we talk about isentropic, it must require two requirements. The first one, the process should be reversible, and the second one, the process should be adiabatic, which means that reversible, no friction, no heat losses, and the process basically can be reversed without leave any trace to the surrounding. Okay, but for the adiabatic, this is the no heat transfer process. So means that when you calculate the Q in or Q out, the value should be 0. Right, so if the process we call as isentropic, means that we need to claim this an ideal steady flow device. Means that if we calculate the efficiencies, or we call as the isentropic efficiencies later on, it should have the value of 100%. But if the process not achieve these two requirement, which means maybe it's not reversible, okay, so the process should be irreversible and you will end up with the efficiencies less than 100%. So it might be 90%, 80%, or much lower than that. Okay, so basically now we know what is ideal steady flow device and also the actual steady flow device. Ideal, it must have a reversible, and for sure it must have the adiabatic conditions, while for the actual steady flow device, it will experience the irreversible process. So the irreversible is due to the friction. Normally it's due to the friction. Okay, but it might experience the adiabatic condition, but due to the irreversible, we cannot say this as isentropic. Okay, so what is the most steady flow device usually operate under adiabatic conditions? So this is normal conditions lah. So for achieve the adiabatic process, we just need to do a proper insulation, and for the ideal process, you will end up with the isentropic, and when you calculate the entropy, the value of S1 will be equal to S2. Okay, so the isentropic efficiencies basically is a measurement of the deviation of the actual process from the idealized ones. So if you have ideal component, you will have 100% efficiencies. If you have actual one, so the process is not isentropic, and you will find out that the efficiencies is less than that value lah. Okay, now how to calculate the isentropic efficiencies? Okay, so we start with first component, steady flow device, which is turbines. The isentropic efficiency of the turbine, if we have ideal turbine, it should have the highest or maximum power output, because that is the objective for why we design the turbine. So if you have ideal one, actual turbine, so you will experience the lower work output. So when we want to analyze these two variation of actual and also ideal, what will happen is that, for example, if you have the same amount of properties, same value of properties, let's say pressure 100 kPa, temperature 100 degrees Celsius, same like the ideal one, if we give 100 kPa and also 100 degrees Celsius, okay, what will happen? Only the output will be different. So pressure to here might be, this one is 20 kPa, this one might be 30 kPa, something like that. So the initial condition should be same, but the output will be different due to the process inside the steady flow device. So it will cause a change in the output. So the ideal one, basically, when we talk about the output, we always noted that particular properties. For example, we want to look into the enthalpy H2. We need to put another subscript of notation here, put 2s to indicate that this process is a isentropic process, which represent the ideal steady flow device. But for the actual one, instead of we just put H2, we put a notation of H2A to represent that process basically is a actual device. So in this case, previously on the turbine analysis, we have calculated the work output of the turbine to be work out is equal to H in minus H out. So if the process is come from state 1 into state 2, so the input will be H1 while the output is H2. So as I mentioned just now, if the process is isentropic or ideal component, so your output will be 2s. So your work out should be equal to H1 minus H2 s. So this is for ideal, while for the actual turbine, your work output will be calculated as H1 minus H2A, indicate that A is correspond to the actual process. Okay, so in order to calculate the isentropic efficiencies for a turbine, we should have we should get the ratio of the actual over ideal turbine work, because the actual work of the turbine always lower than the ideal one or isentropic one. Okay, so this isentropic basically is representing ideal. So that's why the ratio is calculated like that, actual over ideal. So work A, WA here represent the actual one, S represent isentropic or ideal. So when we replace that value, that actual basically correspond to work out is equal to H1 minus H2A, which is here, while for the ideal one correspond to H1 minus H2S, which is this value. So the isentropic efficiencies for the turbine is equal to this formula, H1 minus H2A over H1 minus H2S. So it might be confused with other components, okay, but this is for turbine. Alright, so let me do some example on how to apply these isentropic efficiencies here. Okay, so this question example of turbines, and we analyze for the steam, means that we need to prepare your steam tables. Okay, look at the steam, so standby with A4, A5 and A6 table. Alright, so the question here, steam enters an adiabatic turbine steadily, okay, at 3 MPa and also 400 degrees Celsius, and then leave at 50 kPa and 100 degrees Celsius. So this is steam. It mentioned about adiabatic. turbine. If the actual power output of the turbine is 2 megawatt, sketch the TS diagram and determine. Right. So there's a equation here. The first one is the isentropic efficiencies of the turbine. The second one is the flow rate of the steam flowing through the turbine. So in this case, the question have mentioned about the power output, means that you need to use your steady flow energy equation for this kind of adiabatic turbine. So first of all, you can sketch the turbine. So this is your state 1, and this is your state 2. So inside this we have a steam here. Now you put the properties mentioned in the question. The first one is about pressure, second one is temperature, P1, 50 ppm. Okay, so this turbine basically generate the actual power output. So it mentioned about actual here, means that this turbine basically operate in the actual mode. So you have W dot out, so actual, okay, equal to 2 megawatt. Alright, okay. Right, so in order to calculate the isentropic efficiencies, we need to find the work output of actual and also the work output of the ideal one. So this question already mentioned about the work output of the actual. So we need to find the isentropic condition for this turbine so that we can calculate what is the work output for the ideal turbine condition. So basically or rationally, your ideal turbine will have the greater power output of this 2 megawatt. It will be larger than 2 megawatt. So how to find the isentropic condition here? You must apply the isentropic condition for this turbine. So means that this S1 is equal to S2 should be applied for the ideal process or the isentropic process. Okay, so means that this one, the state 2 given in the question, basically representing the actual condition. So you need to find out what is the state 2s, which representing the ideal condition. So basically for the call as the actual and also the ideal one, the pressure will be similar. Okay, 50 kPa. So the only difference between the actual condition and also the ideal condition is the temperature, which will cause the different value of enthalpy later on. Okay, so here instead of you put P2, okay, you can put P2A, or you can just put it just like that because the pressure is constant. But your temperature you should put here as T2A for the actual one, and for the ideal one you put T2S, which we need to find this. So how to find the T2S here? Okay, we will apply this condition. S1 is equal to S2. So here at state 1, given P1 equal 3 megapascal and also T1 is equal to 400 degrees Celsius. So now given the pressure and temperature, you should look at the table A5. First table A5, find 3 megapascal. Here is a kPa, 3000 kPa. So the corresponding saturated temperature is 233.85. Okay, which is when we compare this one, the value is greater than the T set, means that the state is superheated vapor. Okay, so when we know this is a superheated vapor, look at the superheated vapor table A6 and find the value of H1 and also S1. H1 is useful to find the power output. S1 is useful to relate the state 1 and the state 2 using the adiabatic condition here. S1 equal S2. So you need to find H1 and also S1 in the table A6. So move to table A6. Okay, 400 degrees Celsius is something wrong here. Okay, so the third column representing the enthalpy and the last column here representing the entropy, 3231.7. Other one is 6.9235. Okay, so you are complete your state 1 condition. Right, so the next one is to determine the state 2s, because we still do not know what is the value of the T2s. Okay, so I just put here. For the state 2s, P2 is equal to 50 kPa. So remember, the pressure for the actual and also ideal will not change. Okay, only the temperature will be different. So the T2s is not known, is unknown. So in order to relate state 1 and also state 2s here, we can use S1 is equal to S2. Okay, so means that this is equivalent to 6.9235 kilojoule per kg dot Kelvin. So when you get these two properties, P2 and S2, you can read the steam table. So look at the 50 kPa at table A5. Okay. So now 50 kPa. So your G is 7.5931. Your SF is 1.0912. Means that our value S2 is between SG and SF. Okay, just put here SF 1.0912. SG 75931. Okay, so when you know this is a mixture because it lies between SF and SG. So what you should do is to get the quality of the mixture X. which is equal to S2 minus SF over SG minus SF. So what you will get here, 6.9235. So I hope I get the right value here. So 931, okay, minus SF 1.0912 over 7.5931 minus 1.0912. So put your calculator. You get here 0.897, yeah. Alright, 897. So you can get a temperature here, T2 as, just read from the table because this is a mixture. So the saturated temperature here should be 81.32, okay, 81.32, which is a T2 set. Okay, so in order to get the enthalpy, because we want to get the power output later on, so we need to use the mixture formula, also same like the entropy one, H2 plus X Hg minus Hf. So this is equal to, sorry, this one Hf, so look at 50 kPa. Hf is 340.54 plus X is 0.897. Hg is 2645.2 minus 340.54, or you can also do the shortest one by use the value of Hfg here. Okay, so this is basically is equal to Hg minus Hf, 2304.7. Okay, so what you will get here, alright. So in order to get the power output of the ideal condition of this turbine, so we just put back the formula here. Okay, as mentioned previously, the work output of the ideal is H1 minus H2S. Okay, H1 minus H2S. Okay, so work out for the ideal condition is equal to H1 minus H2S, but since we want to compare with the actual work output here, the unit is megawatt, so we need to use the W dot here. Okay, so how to get power output for in unit kilowatt here, you just put M dot here, H1 minus H2S. Right. Since there is no mass flow rate given yet, so we can just get first the work output in kilojoule per kilogram. So the work out for ideal one is equal to H1 3231.7 minus H2S 2407.9. So we will get 823 kilojoule per kilogram. Okay. So in order to calculate isentropic efficiencies, okay, based on the formula for the turbine, need to use work output in actual one over work output in ideal one. So this is equal to H1 minus H2A over H1 minus H2S. Alright, so since we still don't have the actual enthalpy at state 2A, okay, we need to find this one first. Okay, so since there is a value here T2A, we need to determine from this one state 2A. So I think I put another one here, state 2A, P2 equal 50 kPa, T2A given as 100 degrees Celsius. So look at table A5 and determine the state first. 50 kPa and 100 degrees Celsius. So the corresponding saturated temperature is 81.32. So our temperature is 100 degrees Celsius. Means that this is higher than the T set. So thus this is a superheated vapor. So we need to move to table A6 and find the H2A here at 50 kPa and 100 degrees Celsius. Okay, move to table A6, 50 kPa equal to 0.05 MPa. So the saturated temperature here, 81. Our temperature just now is 100 degrees Celsius here. So end up you get the enthalpy here as 2682.4. Okay, so now we have the value of H2A here. We just put the value as H1 3231.7 minus H2A 2682.4, again 3231.7 minus H2S 2407.9. Okay, now can use calculator. Two four six seven 2407. So I get here the efficiency is around 0.6668, which is 66.68%. Okay, so this is the efficiencies of the turbine. Okay, which answered our first question, and the second one, the most flow rate of the steam flowing through the turbine. Okay, So the mass flow rate flowing through the turbine, we can get from the equation W dot out that's now given is equal to for the actual one is 2 megawatt. Okay, so this formula is related to m dot h1 minus h2a, 2a because it mentioned just now in the question this is for representing the actual work output. Okay, so since we have 2 megawatt here, so this is equal to 2 megawatt equal m dot h1 minus h2a. So what is very important part here is to convert this 2 megawatt into kilowatt, because this unit is in kilojoule per kilogram. So kilo and kilo should be correspond to each other. So 2000 kilowatt is equal to m dot h1 just now is 3231.7 minus h2a 2682.4. Okay, so what we will get here, m dot, you will end up with kilogram per second. Okay. Alright, so be careful with the unit because this is kilowatt. Don't ever put K in your calculator also, okay? Because this one already kilojoule per kilogram. Okay, so this is the example of the isentropic, the isentropic efficiencies of the turbine. And maybe we left with the TS diagram here. So for the TS diagram is quite straightforward. Okay, TS diagram basically looks like a TV diagram. So it means that if you have two value of pressure, you need to draw the two constant pressure line. The first one here, you should have these things, vapor dome. Then at state 1 here, we have 3 MPa. State 2, we have 50 kPa. So only two pressure level. Instead, we have two pressure level here. One is 3 MPa, correspond to the inlet, and the other one is 50 kPa, correspond to the state 2 for the actual and also for the ideal one. So basically, the state 1 here is a superheated vapor, means that it lies in the right side of this diagram around here. State 2A and state 2S. For state 2S just now, I think it is a mixture. Okay, while for the state 2A is a superheated vapor. So for the isentropic, you will have the constant entropy, and this inside the TS diagram, because the x-axis is the entropy, so it means that your line should go straight downward. Okay, so because the entropy is same, S2 S1 is equal to S2, indicate S for isentropic, so that's why you got mixture here. If you don't get the mixture, you need to readjust the diagram. Okay, so sometimes when you sketch, when you go straight downward, you get a superheated, so you need to readjust back your curve here so that you still get the mixture. Okay, so another one for the state actual one, 2A, we get here as a superheated vapor. So superheated vapor 50 kPa is around here. So sorry, just now 2 here you need to write as state 2S. Okay, this one is state 2A. Okay, so how it moved from 1 to 2? A, it goes using the dash line here. Okay, so that's why in your y-axis here you will find out that the 2s, basically the temperature of state 2s is lower than the 2a. So 2s, just now 2s is 81.32. So for the 2a, it should be greater than that, which is T2a is 100 degrees Celsius. And also don't forget to put the unit here, degrees Celsius. For S here, kilojoule per kg dot Kelvin. So this is how you plot your TS diagram for this turbine. The straight line representing the isentropic or ideal condition. The offset on the right one is the actual process or actual condition for the turbine. So basically the ideal condition is just for your reference to know that that is the limit for this turbine, the output, while for the actual one is the what you experience when you run it in the real condition. Okay, that's all for this example turbine. Thank you.